kind of talking about chapter 17 on the study guide, number 4, asking, do you know the mechanism to reform an aldehyde or ketone from an imine or enamine? So basically, this is the reverse process of making an imine or enamine, right? So let's say we have an enamine, right? And enamine's nice because that's a nucleophile, right? An enamine's a nucleophile. Now, what if I want to get rid of the enamine? Let's say I put the enamine on, let's say, so I made the enamine, everybody can get with me there. I used it to, right, bring the electrons down, have the alpha carbon attack, do the SN2, right, and that gets me nitrogen with a plus charge. I've added 2 carbons, right, and enamine's a good nucleophile. I have Br minus floating around, right, and now I'm here, right, and now the question is, right, and then I probably would reform the enamine, right, the H would go, right, because we'd rather have H plus than N plus. So now I've reformed the enamine, and I've added the 2 carbons that I wanted to, so now what? Right?
Question.
Yep.
Okay, so my initial reaction with the BR was then to do like how we do with the chlorine, where we just attack, but it's like the carbonyl, but now it's like an enamine.
Right. So good. So let's say the bromine attacks right here, right?
Yeah.
Let's look at it. Good question. Let's look at it because we're gonna make a tetrahedral intermediate. What's the first question we always ask ourselves when we have a tetrahedral intermediate?
What's the best leaving group?
That's right. So let's look. So let's just pretend. I'm gonna redraw this. So an enamine after it's added a couple carbon pieces. Let's say Br minus attacks the carbon, like the carbonyl. That's going to give us a tetrahedral intermediate. All right. So when you have a tetrahedral intermediate, what do you ask yourselves? What's the best leaving group here? Bromine. And there's no proton around to make nitrogen, the amine part, a good leaving group. So this could happen, but it's going to certainly go, right, backwards. Yep, it's just going to go back and forth, right?
So
and probably going to lie more towards this side.
So when we attack with the chlorine, it's because there's a better leaving group?
Yes. I mean, the chlorine does that with like the SOCl2s. There's a better leaving group there, or one of the leaving groups becomes a gas, and so it shifts the equilibrium.
Thank you for asking that. I have like thought about that so often.
Yes.
Like,
So if you have a gas, you can shift the equilibrium, but you had to have a good leaving group, right? Be careful, right? Because again, ask yourself, what type of carbonyl do I have? Here we have like a ketone, right? Ketones don't have good leaving groups, either do aldehydes. But if it was an ester, that's a little different, right? We have a little more leeway, different things. Or if this was that SOCl2 part, or the SOCl, or we could turn it into a gas and really shift equilibrium. So, okay, good question. So now we're here. We can agree we're here, right? So we went down this path, but it doesn't literally lead to anything. So we've remade the enamine, and now I've used the enamine. I want to get rid of it. How do I get rid of the enamine? It's just the same way you put it on, actually. You're going to use H+, but instead of adding amine, now you're going to add water. All right, so the first step, right, where is an enamine nucleophilic at? Is it nucleophilic at the nitrogen or the alpha carbon? The alpha carbon, good. So the electrons come down and attack. Oops. All right, so we added the new H there. I mean, there already wasn't one H there. We just added a new one. And now we have, right, that nitrogen with a plus charge. It's like an oxygen. That's pretty good. Going to be a pretty good electrophile right here, right? So now we have the water. And the one thing you should be thinking about here, right, an enamine is just an aldehyde or ketone, right, with a nitrogen on it. We can turn it back into aldehyde or ketone. It just takes a little work. Right? So we know this oxygen needs to attack. Right? And notice how we have H plus now around. So we should be thinking, right, what does H plus do? It helps make things better leaving groups, right? That's one of the things it does. So see if I can shrink up this little guy. These guys a little bit. Use up a little more room here. So let's draw this new tetrahedral intermediate. Tetrahedral Intermediate, we ask ourselves, what's the best leaving group? What's the best leaving group here? We just added water, right? But we can have we have a little proton to mess with here though, right? So we're gonna do a proton transfer. So unlike before, where we didn't have that proton to kind of mess with, now we can make something a better leaving group. Right? Now what's my best leaving group? The amine part, very good. I'm going to break this OH bond. Those electrons are going to come down. Go to the H, or go to the nitrogen there. Right, and we get this to happen because we just put a lot of water in there, right? We help shift equilibrium by having a lot of the starting materials. So now we have this ketone, which we've added 2 carbons to, right? And we know enamines are more reactive than enols because the nitrogen is more, right, more willing to donate lone pairs. So it's a more efficient way to do this. We have H plus, right? That's a catalyst, cat. And we have the amine. Right? And notice, right? All equilibrium arrows because, right, this is the same starting materials we use to make an enamine, right? Secondary amine and a ketone. These are the same starting materials we do to actually make the enamine in the first place. And so it's just working backwards. Right? So a lot of times you make the enamine because it's a better nucleophile up here. So you do your reaction with it, and then you want to take it off. And that's what you do here.
That's what's like a catalyst.
It's
But not really.
well, not really. But that's just not really in this case. But that doesn't mean it couldn't be in some cases. But don't worry about that yet. So some nomenclature stuff. Ketones have the suffix -one. Aldehydes have the al, like pentanal. Pentanal, right? Acetone, pentanal. We also have cyclic versions. So this is a cyclic ester. A cyclic ester we call a lactone. So in lab, for the polymer lab, you guys were using lactones. Cyclic esters are lactones. L-lactide is a dilactone, but it's still lactone. Yeah. And if you replaced it, instead of having a lactone and had a amide, a cyclic amide, are lactams. Like penicillin has a lactam in it, a beta lactam. So that's the big difference. Carboxylic acids are acids. Remember that. Remember acid chlorides, acyl chlorides, that kind of stuff. But, yeah.
So like what that would be 1, 2, 3, 4 butyl
Oh,
lactone?
don't worry. I'm not worrying about you naming the lactone. I just want you to know what a lactone is. Yeah, I wouldn't ask you to name this, but yeah, it would be delta lactone.
So like, or would you be asking this if you what was the exam? Like K
Circle the lactone of these. Here's a bunch of molecules. Which one's the lactone?
Okay. What about like common naming? Like, this
I think I did matching on the test last year. Like, do you know what an enol is? Do you know what an enolate is? Enamine.
Yeah.
Okay.
Just for clarification, in case anybody doesn't know.
I'll just not assume that you know.
Okay. This is an enolate. This is an enol. This is an enamine. This is a imine. This is acid chloride.
I know that one.
This is an anhydride. No, I'm not gonna do that in any. I mean, Fine. This is called an iminium, but I didn't talk much about this, so.
Wait, what's the bottom one?
Anhydride. Imine, enamine, iminium, enol, enolate, lactone, lactams, ketones, aldehydes, als, pentanal, butanal. Those are aldehydes. All right, let's kind of examine a molecule, the same molecule, same starting material, with two different reagents. One will use NaBH4, and then acid. And we'll take the same exact molecule. And in this case, we'll use lithium aluminum hydride, LaH4, and then H+. So what we're trying to get at here is a couple things. So both of them are H4, meaning they have 4 hydrides, right? 4 hydrides, right? So this is a 1-to-4 ratio, right? So we actually have an excess of hydride here, right? Just starting out, we have 4 H minuses. Now, is every H minus created equally? Every H minus is not created equally. So which one of these is more reactive? And the way to remember this is, which one did I let you use in lab? So is that the one that's more reactive or less reactive? Right. So yeah, of all else fails, remember I only let you use the more safe stuff, right? But why is the BH bond different than the aluminum H bond? What's the difference? Less orbital overlap for which one?
Less orbital overlap for the aluminum.
Right, because the aluminum's
Humanosaur.
bigger. It's this bigger than boron, right? It's one row down it's one row down on the periodic table. So aluminum's bigger, so there's less orbital overlap. So that's going to be a more reactive H minus source. So why does that matter? Okay, well let's look at this. We have 2 different types of carbonyls, right? We talked a lot about which carbonyls being reactive and not reactive, right? We have a ketone and an ester. Which one is more reactive, an ester or a ketone? The ketone is. Why is the ester less reactive? Like when I say reactive, we're always talking about the carbon of the carbonyl group, right? Why is an ester less reactive than a ketone?
Move the charge around.
Because the ester will move not just a charge, but move some of these electrons around, where you don't have this be so delta plus, right? We can move electrons around, right? Okay, so an ester is farther down Mount Carbonyl, right? It's more stable than a ketone, right? We have to match, right? Now we get to the point, now we're getting sophisticated enough where we have to match our nucleophiles to our electrophiles, right? So if we have a nucleophile that's not that reactive, which electrophile will it react with? Only the more reactive electrophile, right? If this isn't that reactive and this isn't that reactive, no dice, right? So in this case, only thing it reacts with is the ketone.
So we had a question like this on the
Take-home quiz, yes. Yep. And sodium borohydride only reacts with ketones and up, right? So it won't go for an ester. It'll go for ketones, aldehydes, and like acid chlorides, right? But it won't get an ester. Esters are too stable. They're not electrophilic enough. Now, the other side of the coin is now you have lithium aluminum hydride. And remember, we have 4 H minuses, right? And we only have two carbonyls. So we have plenty of H minus. We're already fine. The real question is this reactive enough to reduce an ester? And it is, right? And it's going to add twice, right? So I'll draw this first part, right? It's for sure going to get the ketone, right? The ketone's already reactive, you know. And in this case, you're going to get these 2 species. Let's look at the mechanism for this. Right? I'm assuming we know how to do the ketone one. I'm not going to worry about that. So H minus attacks here. What do we form? Tetrahedral intermediate. This has already been reduced, let's say. So now we have O minus. We added the H. And what do we ask ourselves when we have a tetrahedral intermediate? What's the best? Is there a leaving group? And then if there is, what's the best one? What's the best leaving group here? The methanol. Kick out the methoxide. Yep. Out that goes. So still O minus, right? We're in base, right? There's minus charges around. And now we've created what? We've turned the ester into a aldehyde. By God, aldehydes are more reactive than esters. So you think this aldehyde is going to sit around very long? Nope. Right? It's just like it's the same idea when you have Grignards with esters.
Yes. I'm right. No.
O minus. So we have a tetrahedral intermediate. We ask ourselves, what's the best leaving group? Is there a good leaving group? No. You're done. Go to step 2. Step 2 is where the H plus comes in, right? So everything, sorry I didn't draw this. This was in here along for the ride too, right? Everything just gets protonated, and we get all the alcohols back out. But lithium aluminum hydride's reactive enough, and there's 4 of them, right? So how many hydrides do we have to use here? We had to use 1, 2, 3, right? We still even had an extra one left over. Right. Good. Let's have some fun and take that same starting material and pretend we could take a really big bulky base, say tert butoxide, and know what's going to happen, right? So again, we got to think about bulky base. What's more reactive, a ketone or an ester? Ketone is. Now, some people might say, well, couldn't this negative charge attack here and kick up? No, it could, but again, there's a reason why I picked a bulky base. How well is it going to be able to get in there? Probably be tough. So I'm going to say it's going to work on the ketone, and it's a base. So I'm thinking alpha CHs. I have 2 different types of alpha CHs. I have a bulky base, so which alpha CH do you think is going to be easier to get to? Is it going to be A or B? A, right? It's less substituted. She'll be more sterically accessible. So let's have this negative charge go there. Kick up.
Can we pause for a second and we're done with
Yep. So let me draw this enolate out. There you go. Okay, so now we have the enolate, and now it's a good at this point to kind of count some carbons. Let's go 1, 2, 3, 4, 5. So 5-member rings are suitable, right? So for a carbon molecule. Basically, at this point, right, we say, well, I mean, even if I didn't, I could deprotonate here, but from a 1, 2, I'll never make a 3-membered ring, right? So within one molecule, I have my nucleophile, carbon 1, and my electrophile, carbon 5. Electrons come down. Don't forget the electrons have to come down in all of these, right? Whether it's an enamine, an enol, or an enolate, make sure you bring the electrons down. Attack carbon 5, kick it up. I made a 5-membered ring, so I'm just going to draw a 5-membered ring. I think this is the easiest way to go. Draw a 5-membered ring, right? Because I counted the numbers. I'll make this carbon 1, carbon 2, 3, 4, and 5. And I'm just going to fill in what's on those things. So carbon 2 should have what? A double bond to O. Carbon 1 and 5 is a new bond I formed. What else is on carbon 5? There should be a O minus and a O methyl. Am I missing anything else on 3 and 4? Looks good. Right? But I think that's the easiest way. I made a 5-member ring, draw a 5-member ring, fill in from there. A good numbering system always helps. So now classic, we have a tetrahedral intermediate. What do we ask ourselves? What's the best leaving group? Do we have a leaving group? By God, we do. Electrons come down, kick out the oxygen, and we make a diketone with O minus there. The way to cyclize, yeah.
Why are these not equilibrium arrows?
They are equilibrium arrows, sorry.
Do we need to, like...
I when in doubt,
Like how?
I haven't been a big sticker on the arrows, right? In the situations where you generate a gas, I want to make sure you know that's a one-way street. That'd be important.
What are the gases that we should know?
The SO2, the H2 gas, when you have lithium aluminum hydride reacting with
do that one?
carboxylic
We
acids.
also have CO2.
Yep, you make CO2 in the decarboxylation reactions. So anytime you generate a gas, we've seen H2, CO2, and SO2. Those are for sure one-way streets. All right, this is looking at a sapling question from 18, number 20. So we have this weird-looking cyclopropane guy. And we have this dicarbonyl. And the first step they're putting in here, they're saying Na plus, they didn't put the plus, O minus ethoxide in ethanol. Okay? So this is where it gets tough. Right? This is where things get hard because all of a sudden we have three things and we got to figure out what's my nucleophile, what's my electrophile most likely, right? So can we identify one of them being the most what species in here is the most reactive?
One.
Na plus.
The O minus, the ethoxide, right? Something with a charge is going to be the most reactive. So that's going to be my nucleophile or electrophile, the O minus. Nucleophile. Okay. Now I got to decide which one of these is the best electrophile. Okay, so one of the first questions we ask yourself, we decided this is my nucleophile. We also should decide that these are basic conditions. I know there's an Na+, but anytime you see an Na+ or a lithium+, they're essentially along for the ride. That really we'd never do anything with those. So really we consider this basic conditions. So minus charges, right? Minus charges overall always. Now we could do an SN2, or, right, we could deprotonate this dicarbonyl. Remember we talked about dicarbonyls? This this bond being very reactive because it's getting pulled two ways. So let's do that. Let's deprotonate and make a nice enolate.
So are we doing that because it's more reactive?
We're doing that because it's more reactive. And usually what I would probably say, step one, in reality, if you're doing this reaction, I would have this and this mixed together in the round bottom, and I would slowly add this in, right? I wouldn't probably have all three of these things mixed together, right? Practically speaking, I would take some time, make the enolate, then add in the electrophile, right? So now we have a nucleophile, right? And this carbon bromine, right? Is that carbon right there electrophilic? Yes. So let's just do like an SN2. And I know that 3 number rings there and it looks weird, but it's okay. You can have cyclopropanes. They're not fantastic, but you can make them. They're in drug molecules all the time. So there's nothing wrong with that. So we're done at this point, right? That's it.
I mean,
It's not it. There's more to go, but this first step is over.
oh, okay.
The first step is over. Okay? So let's shrink this down.
Can I, well. Nope, never mind.
Yep. So the whole point of this was, right? The whole purpose, if there is a purpose in anything, right, was to deprotonate this, right? Make this, right? You see these carbonyls, right? Again, we see a O minus. We see these carbonyls, right? And since there's 2 of them, we know that's really acidic, right? We talked about the pKa's. And then this is always an electrophile, right? Carbon tetrabromine, that's an electrophile. Don't worry about this, the frivolous 3-membered ring here. Just trying to trip you up, right? Okay. It gotcha. Don't let it get you. Okay. But we're not done. We have another step. We have 2 more steps, actually. Now we're going to have step 2, NaOH minus. Well, what the heck is this going to do? What will this do?
Take another alpha.
It could take another alpha H, but so I could deprotonate, but are there any electrophiles in here, really? What's the easiest thing for it to do?
Better leaving. It'll attack the 1 carbonyl.
Right, so actually you notice, ooh, I did this wrong. I messed something up. Right, this was actually ethyl. So there's a reason why we chose ethoxide. Because this could attack here, right? And this is exactly the same as this, right? So even if it did that, it wouldn't change anything, would it? But notice if I make it OH, why I couldn't use OH minus here, because if I use OH minus here, what would this have turned into?
That would have changed.
A carboxylic acid. But yes. So the OH minus can attack that carbon, right? Just like this ethoxide could have done that. But if that ethoxide attacked, does it change anything? Doesn't change anything. So there's a reason why, if you've ever noticed this in your problems, whatever's on your ester, the base you usually use has to match it exactly. Otherwise it'll change. So you gotta be careful in your reactions when you do this. Have you noticed that? So this is ethoxide, so this had to be an ethyl piece. But now if I put OH minus in now, because right, this could certainly attack here, but it's not gonna change anything. But now if I put OH minus in, it does change things.
Are you still missing a carbon then though?
God darn it. I was. No, I think we're good. Tetrahedral Intermediate. You ask yourself, what's the best leaving group, or the most likely leaving group, of course. And I would say, right? In this case, right, I would say you add a lot of OH minus. Right? This would be, to be fair. Right? Why else would you put it in there? Right? It's got to do something. So let's kick out the ethoxide. And what have we turned it into now? We've turned the ester into a carboxylic acid. Right? And that's using basic conditions to do that. Right? Overall negative charges. We could do it in acidic conditions, couldn't we? We could just as easily have protonated this and added water in and done that whole thing. This is just basic conditions. So there you go. Now we're the carboxylic acid and we're done with step 2. But we're not done yet.
Is there a reason in lab that you would choose to do acidic over basic?
Yeah, absolutely. So like say like your molecule, so pretend, right, these are pretty small molecules, right? But if you were in a big drug molecule, right, there might be some sort of crazy or sensitive functional group someplace else that are really sensitive to acid, and so you'd want to use the basic conditions. Or molecule might be sensitive to base, so you want to use the acidic conditions. So there's all sorts of reasons why. Absolutely. Right, so it's always, we're trying to get multiple ways to do similar things in different conditions, right? So the last step is just H plus, H3O plus, and heat. Uh-oh. What does that mean? Everybody should recognize that one. H3O plus and heat, that's going to be one of our gases we're going to make. We're going to lose CO2 now. Yay. Right, so how are we going to do that? So let's see. Let me make sure I do this right. So we're going to do this decarboxylation, a couple major things. You need 2 carbonyls to do this, and they have to be 1, 2, 3 carbons away from each other. So that you need 2 carbonyls. If it was just this by itself, I can't do the decarboxylation. You need 2 carbonyls. And we'll see, when we look at the mechanism, why that is. Right? There's a real reason why. So I'm gonna redraw this in a more suggestive manner. Right? In a little more suggestive manner. So if you look at this, the carboxylic, so you see this, you just think, I'm going to lose CO2, and this is the CO2, right? We're going to lose CO2 right there. That's the CO2 we're going to lose. So what's going to happen? First step is that pi bond takes the H.
So even though if we take an H off of and make water, it would gotta take it from itself because it's
Intramolecular, right? This is all intramolecular. We haven't used the acid yet at all. That breaks this OH bond, which is good because I want to turn this into CO2, right? Which has a C and 2 pi bonds. And now this is why, the next arrow I show is why you need to have that second carbonyl. Because so this just lost electrons, right? If I number these carbons, 1, 2, 3, 4. Carbon 2 lost electrons, right? Everybody see that? So that means carbon 2 needs some electrons back, right? So it needs to get them back, and we need to break a carbon-carbon bond. So a carbon bond between 3 and 4 actually breaks. And we form a new pi bond there. And we end up making an enol from this. So let me shrink up a couple of these. So what does this look like now? OH pi bond. Oh, nothing there. That is gone. Oops, darn it. Ignore this. Nothing there. It won't. The eraser won't. It won't work sometimes. So erase that, but now I wonder. Yeah, see. That's a phantom bond. Nothing there. So make sure number of carbons 1, 2, 3. There's 4, right? And now we need the H plus, right? So now we have an enol, right? We see the enol, and now the H plus can come in. And where's an enol nucleophilic at? On the oxygen or on carbon 3? Alpha.
I'm totally gonna forget that.
So that's your final product. One-way arrow making, you make that CO2 gas, and it's over, right? Out it goes. That decarboxylation. How do you find it? Dicarbonyls. One of them has to be a carboxylic acid, and H plus and heat. You can also do it in base too. Yes.
Will it proceed if it's 4 carbons away instead of 3?
No. It needs to be 1, 2. It needs to be just like this. Just
Just
one.
like
This 1, 2, 3. This carbonyls like this, right? So that's why we look at a lot of these carbonyls that are right next to each other with a middle space, because they're super acidic. They're more acidic than normal, and there's a nice way to get rid of carbons if you want to get rid of a carbon for some reason.
So when we,
Yeah, when you see this and you see probably heat as well, that you should think, well, I'm gonna push it, right? Heating something up, right? Right, because really, why does this take a lot of energy? Well, one of the things to think about, where we broke a carbon-carbon bond, right? Those are pretty strong bonds, right? So we're going to take some heat to get there. Now, once we get there, it's over, right? Because once I make CO2, there's no going back.
Yeah.
But it's just going to take some juice to get there. So that's why you need that heat. All right, let's look at situations, right, when we generate gases, right? So we have a lot of trouble, right? We do a lot of one-way arrows, right? So things that have one-way arrows are Grignards, things with C minus, that'd be a one-way arrow. H minus hydrides are one-way arrows, or anytime we generate a gas, right? So one of the ones right off the bat, for sure, is a one-way arrow. If I have this in lithium aluminum hydride, right, which is like H minus, and that's my step 1, right? Amides are really strong, right, really stable, low on amount carbonyl. So we need the really strong reducing agent, really need the really strong reactive H minus source. But the first step in this reaction, H minus takes the N, H, takes the H from there. And that's a one-way street. Why take the NH? Well, it's a polar bond. Also, the product we make can be stabilized by resonance. And what product did we make? We made H2, which of course is a gas. Right? And so either you have, right, this is a polar bond, right? Hydrogen and hydrogen form a pretty strong bond together, so that's a good bond to make. And the product we make has resonance. Now, am I going to stay like this? No. So I might as well go through this mechanism over here. Let's draw the resonance form of this. Why not put the negative charge on the oxygen, right? It's happier, it's more electronegative with that. What else do we have in there? We use one of our H's, right? One of our H's has been used. What's our overall charge here? Are we in acidic, basic, or neutral conditions here? Basic, right? Minus charges, right? So we have an O minus, so that's probably going to be our nucleophile. And only thing left to have in there is aluminum. Does aluminum have a full octet? No, it only has 6 electrons around it right now, right? So let's have this attack that. Minus aluminum. Now aluminum has a negative charge. Even though the aluminum has a negative charge, right? Lewis dot structures have been known to do what to us? Lie. It's a liar. Where's the electron density really at? Is it on the aluminum or where is it at? On the hydrogens or the oxygen. But now, right, this is kind of primed where here's an H minus, and that's like a carbonyl carbon. Boom. Have it attack. Make sure we want to do what? Every step of the way we got to balance our charges. Oops. Where should there be a negative charge now? And the nitrogen should have an N minus, right? And this looks awfully like what? Or it is, right? We went from something that was sp2 hybridized to now it's sp3 hybridized. What do we call this? A tetrahedral intermediate. And what's the question we ask ourselves with a tetrahedral intermediate?
Why is mental aspect?
Do we have a good leaving group?
Why does AO not have a charge?
Because it just lost the H. Right? So there's a negative charge there, and the H is what attacked there.
Okay.
And so now the negative charge, right? The electrons went, you can see the electrons kind of flowing here and then end up on the nitrogen.
Okay.
So now the nitrogen is a negative charge. So let's have that guy bring its electrons down. Go there.
So the O group is the best.
Yep, aluminum and oxygen want to be there. That's a strong bond. They want to be together.
Should we make it a double bond, or should we have it as a?
I'm going to show it as a double. I'm going to show it as a double bond here, but you could just have another lithium aluminum hydride come in. So I'll show you one way this could work. I'll shrink that down. So we've made, what have we made here? Imine. That's right. Imine. Now the aluminum has a double bond to oxygen and two H's left. So where's the negative charge at? Who has the negative charge? Aluminum does. But again, where is the actual electron density at? On the oxygen or the H's? And I'm going to say the H's here, right? Another H comes, attacks. What do we have now? Now we have the nitrogen, the negative charge. We've added the second H. We have the aluminum. That's not charged anymore. This looks like a tetrahedral intermediate, right? This was, right, sp2, now it's sp3. Tetrahedral intermediate. Do I have any leaving groups? You're done. So then you go to step 2, which of course step 2 was H plus. Takes that H plus, and the final product is an amine. Right, so you take an amide and turn it into an amine in this case. So if we're on the subject of gases, another version of this is our old friend SOCl2 and a carboxylic acid. And what this will do is turn a carboxylic acid into an acid chloride plus some HCl and then SO2 gas. So right, where we generate gas, the step we generate the gas, of course, that's a one-way street. Once we make the gas, we bubble it out, we're not going back. So the first step here, we got to decide what's my electrophile, what's my nucleophile. So so the carboxylic acid is kind of weird, and maybe I'm not sure what's that going to be. So let's look at the SOCl2. What is that going to be, do you think? Electrophile. That's sulfur. Think about that sulfur. It's got two chlorines pulling on it, and oxygen don't bond to it. It's going to be pretty delta plus. So I'm going to take this one, kick up. All right. We know we can't do SN2s on sulfur, right, if it's sp2 hybridized. I may have been a little lenient on the quiz about that, but I won't be later. Sulfur, oops. S, O minus, Cl, Cl. So it looks a lot like, to me, like a tetrahedral intermediate. Right? So there's a couple things you could do here. You could just have the sulfur kick its electrons down, kick out the Cl. I can't really do a proton transfer onto a chlorine, can I? Right? No. Plus charge S Cl. So now I could do a proton transfer here and say, well, I have the proton, maybe I want to do a proton transfer to make the carbonyl oxygen that much more electrophilic, which would make this carbon more delta plus. So I do a proton transfer. Remember I made Cl minus here. So there's a plus charge there. There's Cl minus. So why did I effectively do that? I was making this carbon that much more delta plus, right? Now the chlorine can attack, right? Because we know what we're trying to get to, right? We're trying to get the chlorine here, so I want to get the chlorine on that carbon. I attack that sp2 center. What's it going to turn into? Tetrahedral Intermediate. Equilibrium arrows. Tetrahedral Intermediate. Right? We ask ourselves, what's the best leaving group?
Definitely big sulfur octane.
So the chlorine is a pretty good leaving group, but let's just say every so often, right? This OH bond breaks, these two electrons go there, and we kick out that chlorine, right? And here it is, there's that one-way street arrow. The Cl. We have the O, SO2 gas. We had the H plus made. And we also made the Cl minus. So there's your HCl. But there's that one-way street. Now we have the acid chloride.
So is that last step, that every so often concept, is that a thermodynamic or is that a kinetic?
Oh.
Because it would be thermodynamic, wouldn't it? Because that gas is the most stable. And it's
Yes.
increasing the most entropy, so all the energy is there.
Yes.
Okay.
This would be downhill. But it's going to take a little bit of time, take a little bit of energy, a high hill to maybe get to this.
Yes, right.
But this would be the more because the gas is going to be
But
stable.
in the end, it is.
Yeah, so it'd be like a thermodynamic process.
Okay.
Yes, I think you'd be right.